Okay. Hi, everybody. In the previous lecture, I have introduced to you the library of machine learning, which is called PLAIY. I have told you that PLAIY was developed by Technology de France group, and it is a very new library. It is only 2 years ago. It is not published officially yet, but those who want to work with it can find it in the repository of GitHub. It could be downloaded from there. I am recommending you this library because it is an open source. This is the most important. And another important thing that it is really easy to use and has a large number of virtual instruments that can be utilized in machine learning, such as in regression tasks, classification, or clustering. We have illustrated for you an example using the PLAIY library for linear regression and compared the results with those we found when utilizing Python. And we found that we have got the same results without any complexity and no problems. In today's lecture, I am going to work on PLAIY library in detail so that it will be more familiar to you and you can use it easily. I shall illustrate for you 3 examples, and if time allows, I shall illustrate for you the 4th example also. So let us begin with this example here. This is the block diagram. And as you see here, we are going to work with a data set which is related to Boston housing file, which I have downloaded in the previous lecture. This is the path to the file which is downloaded, and this is the path shown clearly that it is existing in the documents of this computer. Okay. Now, at the beginning, I want again to familiarize you with the used virtual instruments in this program, and then I shall investigate this program step by step for you. So the first VI here, as you see, is the split data set XY VI. This is used to split the data set into 2 main groups: the training group, which is X train and Y train, and the testing group, which is Y test and X test. And usually we give a proportion value which is showing the percentage of the testing group relative to the whole group. Usually it is taken, and the default value in this program here is 20%. And 80% of the data will be used for training. How to find this? You right click on the block diagram and go to the TDF library, PLAIY. Here you go to the split data. This is a subpallet, and another detailed subpallet here also related to splitting the data, like k-fold, for example, VI, or like, let me show you more common, the group k-fold, for example. And this is our VI of interest, which is called split data set XY. Here it is shown on the block diagram. I have selected the regressor of the group SVR or SVM in general, and SVR really is the support vector regression algorithm, which comes under the SVM. Anyhow, to find it also, you can right click on the block diagram, go to the TDF, go to the PLAIY, and from there you go to the machine learning, and here you find supervised plot, supervised group, and you go to regression. In regression, you will find another subpalette here. This is the linear SVR algorithm, which we will use in this program. So again, it is not that difficult. You open the PLAIY, go directly to machine learning. In machine learning, it is divided to two groups. One of them is supervised and the other one is unsupervised. We are interested in regression with supervised, so I have selected or pointed to the supervised, and then I went to, or show the regression, and within the regression palettes, I have selected the SVR. Of course, to select another VIs, the rest of the VIs which we have here, we can do the same. But I want to tell you that when you go to the machine learning, you will find most of these VIs which are related to this subject near to each other. So if I right click and go again to the PLAIY and to the machine learning, we will find here beside it, this is the initialize VI. This is the set parameters VI, which we use there. And this is the get attributes. Here it is. Yes, it is here upwards. Get attributes VI. And also we can find the other VIs used in this example. In this example, yes. What we can see, this is the last one, which is the closed session VI here. This is the get attributes. We can see also the score. If you go to the PLAIY here, here is the metrics and scoring. It could be somewhere here or here. It is not shown. You didn't find it. What you can do then? There is another more simple way to do that. You go to the SVR, or not to the SVR, you go to this router, right click it. Sorry, you will see now. You will see here nuSVR pallet. Directly, you will find this pallet appears with most of the VIs which could be used with this SVR. One of them, as you have seen, is the predict. Here it is. The fit is here also. The score is here also. Get parameters, set parameters. Any of these VIs which could be used by this algorithm. For example, you need the score, you just click it and it, sorry, again. Here it is. You just click it and it will be there. And then you can use it. So by time, you can learn exactly how to use or how to find the virtual instruments directly, moving from one pallet to a lower level pallet to a lower level pallet until you find what do you want, or you can right click on the cluster type or the router type here, and it will give you the whole set of VIs which may be used by your program. Okay, now we have learned much better about the PLAIY components or how to place them on the block diagram. Now, again, I want to go back to show you about the data set. The data set itself, which I have already saved in the documents, is read by using the read delimited spreadsheet VI. This gives you two-dimensional array, as you see here. If I right-click it, you will see this is the data set. It consists, as I told you in the previous lecture, of 14 features, 14 columns you have here, and 506 rows. As you see, this data set has a first column, sorry, a first row of zeros. It must be deleted at all and not used. Secondly, we have to divide the whole data set into two parts as usually. One part which has included or which will include all the features except the feature which is selected as a target. In our case, we are selecting the target as the last column here in the table. So we need to delete this column, and the rest will be considered as the X values, and this column alone will be considered as the Y values or the target values. To do this in LabVIEW is easy by using delete from array function. Delete from array function is found, you can write it, you go to the arrays here. Here is the delete from array function. So it appears here. Of course, you can just directly, you can directly place it on the block diagram and connect it with what you want. Now, how it works also is not difficult. You define the index of the element which you will begin with, I am going to begin with the index 0 and the number of elements which you will pass through. The length, here it is the length. I want to begin with the first row and to move only one row. This is the length of moving. So I need to delete only one row beginning from the 0 indexed row. With this, I deleted the first row which contained only zeros. Then I used another delete from array element or function. Here I begin with the index number 13 and delete only one column. Here is the columns, as you see. If I put the cursor, you will see index of the column. The upper one will be index for the rows. So I have selected the index of the 13 column, which is the column number 14 in general. I want to delete it, and the length will be 1 because I want to delete only one column. So deleting with this column now will leave for me the rest, which is 13 columns, which represent the features. If I click on this is the size of the left or remaining array. If I click it here, we shall have the size. I don't know why it is not shown. Now it is 506 rows and 13 columns. Here it is. This is our X array. The array which is taken before at first, here it is, of the columns. I go back to the block diagram and show you. So this is the whole set which I have, the whole set. I pass the whole set to the delete from array function. Here I want only to begin from the 0 column and delete only the 13 columns before it, so that I shall have at the end only one column which represents the Y array. So at the output here I have Y array connected to the Y input of the split function and the X array connected to the X input of the X array. And also I have fixed 80. Of course, you can change from 80 to 75 or to 85. It depends what you find better, but the default value is 80. And here is the column which we have, just the size of the column, 506 rows with one column, which represents the target. So as you see in LabVIEW, it is easy also to work with in order to divide the data set into features group and the other group with the target group. Of course, you can have more than one target depending on the situation. Now, the output of the split data set XVI, as you see, is splitted into two groups, and these groups now must be fed to the regressor. Here in LabVIEW and with the PLAIY library, the setting of parameters is not done through the use of the front panel. We really use the nodes, the property nodes. Here is one of them, and here is another of them used. Let me show you. Okay, property node. This is the other property node. So the data of X training, the X train and Y train are fed to the terminals of the property node. The property node only exists, as you see on the block diagram. It is considered as an interface, and it is connected to the initial or initiation of the regressor and with the regressor itself, as you see here. Now, if we look at the, I wanted to show you this. Oh, I'm sorry. I want to show you what is hidden here behind this arrow. I have selected to work with nuSVR. This means that I have many options in the SVM regressor. If I click it, you will see I have linear SVR, or I have only SVR, or nuSVR. These are different modifications of the SVM regressor, and we shall try them a little bit later. So now the data is fed to the SVR. If you want to be sure and to see the data, of course, you can click here. Maybe I have done something for you or not. No, I didn't do that. If I click here again and go to the new SVR, which is our regressor there, I can select from here the function which I can use, which I need to read data. For example, read data VI. This is a function. If I connect it here with this root, I can read the data outside here by an indicator. Create indicator, and you will have, for example, an output here. This is large. I make it as an icon, and here it is shown alone to read it. Here it is, it gives you the output as Y output. Of course, you can also read the X input. No problem with that. Let me show you. I right-clicked it, new SVR. I am here now. Now, there should be something related to X. Yes, read X data VI. Here it is. I can put it here or here, and then I can connect it again, and I can read the output from here, an indicator. And now this is the indicator here of X. And now if I run the program, I can read the values which are here. Now it is still running. The program is still running. Now after a while, it will give you the values which are read here. So only I have to put it. Okay, let me shift this one here and shift it a little bit here. And now I can open it. And as you see, it should give me again, trying again. Let me take away this one to make space for it. Now I have to like this. Now It doesn't show. I don't know why. Anyhow, it should show. What about the Y? Maybe the place is not appropriate there. Okay, let us go back and connect it here with the output here. It is coming here and going there. Okay. Well, this is the set parameter. And now, if I go back, yes, it is. So I have the values of X and I have the values of Y. So as you see, the idea is not that difficult. You can, in detail, investigate the block diagram which you have and define the values at every stage by using these helpful functions which are associated with the working regressor. Okay, now after having that, as you see, the values are set or assigned to the regressor, and also I have fed the other property node with the X test value so that I can make so that I can make predictions. Here it is fed to the predicting VI, and also I have to use the Y testing for drawing and also for estimating the score by comparing the Y predicted and Y testing value, the input and the output. So these also are fed there, and as I told you, I can see them also by doing the same as I have done before. So the output, as you have here in this point, C, is the Y predicted values, is an array, two-dimensional array as shown here, of the predicted values for the given input, which is, of course, X test. If you want to see it, just double-click it here. You will find these are the predicted values. And these are the values of the Y test. And you can compare by eye and see that they should be close enough to each other. Every point, every relative points should be, this is 16.7, this is 16.6, this is 19, this is 18. This gives you a sense that the work is normal and there is a high degree of accuracy. Okay, now we have predicted the values and we have a score at the output which shows the degree of accuracy, and this score here is given as 0.804, which is really very high and very acceptable. Also, for your knowledge, I have calculated again the score by using simpler functions. Here I used the Y test array, converted it to a one-dimensional array. Now these are the values contained here of the array. I found the mean value of the array, subtracted the mean value from each of the values of the array, and I found the deviation. I squared the deviation and has taken the sum of the deviation here. Again, instead of finding the deviation, I find the difference for each relevant points of the predicted values and the testing values. And I found these values here. I have squared them and found the sum of them also. Then I have divided them by each other to find X minus Y, which is practically the value of the score. So the score here should be exactly the same as the score which is found by the program, because the program does the same thing indeed internally. What else I can tell you? Now I have taken the predicted values and input it to the indexing terminal of the for loop, and the same thing I have done for the y test values in order to plot the graph which is shown here. The graph shows the data set y test against x test and y predict against x predict, sorry, y predict against y test. So as you see, the location of the here, of course, it is given as a line just to show you. And now you can, no, I should here change it. Now you can say the distribution of the data set, the original data set and the predicted data set relative to X test. So what we can say at the end, we can say that the work here is giving a normal result. The distribution of the plot, scatter plot are very close to each other. And this is manifested, of course, by seeing this figure here. And now maybe it is time to have a look also at the other options or modifications of the SVM regressor. I am working with a new SVR. Of course, I can move to another one. Let us work with the, for example, linear SVR. No. Let me go to the SVR itself. When working with the SVR only, here I have ignored the linear SVR. Now I am working with SVR only. As you see, this is a wrong thing, showing a problem. I click it and cancel it. Again, back. Here, I cancel it and then create it again. All what I have to do to create it again, create control. Now this control here exists. Here I shall have another control relative to the, not the new SVR, but to the SVR itself. And now let us try to remember what we have got. Here the score was 0.8, 0.8, and you can have a look and remember the shape which we have got before. If I run it now, again, with using the SVR only, now it is running, now it is finished. Now you can see that we have got a new predicted values, and of course a new distribution, and of course there will be a new value which is given 0.22. This means that the first algorithm was working better, and really I considered it as the default for me. This is seen here by you because all these scattered values are far away from the predicted values and the error become higher really. The first one was closer to the real data set which we have from the Boston housing. What can we do also? Let us try to consider here the kernel is RBF, which is usually used when we have nonlinearity. Now, if I try to work with linear option here instead of nonlinear, what can I get? Let us run it and see. Now it is running. Now we have got a very high score, 0.777, and if we come here, we see that curve and the distribution is much better and closer to the original data set, which means better score. Let us try to change the degree. Normally the degree is used with the polynomial. It should have something like polynomial. This is the polynomial option. And now let me put, instead of 0, 3, 2, 3, or 4, or 5, no problem, and try the polynomial option and how the errors will be shown. So I run the program again, and let us see what will happen. It doesn't work well. It gives, as you see, this distribution, which is similar to what we have got before when we work with the SVR, and this is not good. Let us try, maybe we can improve it by hiring the degree of the polynomial. Let us hire it, make it, for example, 7 or 8, and try the score now 0.08. Run it again and see. Now it is improved, 0.2. And of course, here you can see that the curve has moved a little bit up and it is more appropriate than the previous one. Let us try to raise up the degree also a little bit higher. Let it be 12, for example. Maybe it is acceptable, I am not sure. Now it is much better, 0.288. Yes, it is much better, as you see. So the idea now is clear for you. You have a large mobility, a great mobility to work with. You can select any modification you want, SVR or nuSVR. Of course, for nuSVR, I have to change this again back. Or if I finish with the program and don't save anything, it will come back again as it was before. Anyhow, I prefer to take it away. I didn't use the linear SVR because we have used the linear regression in the previous example. So just finishing with this, going back, creating again, and now you run it newly and you will get the same results. Run now, this score will change to about 7.7 or like that. No? Oh, yes. Again. Everything is okay here. So we need to go back to the, sorry. Here is VR. It is not a new SVR, no problem. We go back to the degree here is about 0 or 1. It is 1. And I think the new is 0 and so on. How to know about these things here? It is not difficult. Let me tell you how to do it or to know about it. You just right-click on the SVM regression VI here, right-click it, go to the help, and then you will have this sklearn original algorithm with information about it, because what is in the PLAIY, in the PLAIY really we have only a conversion of the nuSVR, which is in sklearn, to be as a virtual instrument to be used in LabVIEW. So here you can have the syntax of the nuSVR, and you can find that the coefficient of nu, the default is 0.5, C is 1, the kernel is RBF. This is the original and the best thing to work with. So it is not linear. So if we go back now to our case here and go to the front panel, and now the kernel is RBF, nu is half, everything should be as okay. I didn't change anything here now. And if we run it again, it is good, but not that good. Let me change the C from 1 to 2 or to 3, the coefficient to 3, for example. Now, not that good, but maybe concerning the tolerance, here it is 0, 0, 1. Let me make it less by 1. It is now 0.4. So as you see, you can improve. Let me make it a little bit higher, 5 maybe. You can improve the results as you want. You have a large possibility. If you go back, let me go back and don't save anything and try to come back to the original one. File, open, save. This is the 7, our program as original one, which we have. So what I have, see, it was 4. I try to put it 5 now. The degree was 3. And that's it. Now, if you run it again, okay, it is okay, normal, no problem. So, shortly speaking, now I can summarize what I have done up to now. I have introduced for you the PLAIY library with detail, how to display every element or to select every VI from the main library or from the subordinate library, which is related to the used regressor, how to modify the data set in the direction you want to be splitted, and how to configure the coefficients of the different modifications of the used algorithm. I think for now it is sufficient. In the next lecture, I shall go further and work with you using the regressor and its different modifications. Thank you for listening and wishing you the best.